Yeah. So let us start with a just quick recap whatever we have done in previous lecture. We have introduced the definition of random variable, and we have defined in this way that a random variable is a function from sample space omega to R. Remember, probability is a function from the sigma field to 0 to 1, but random variable is a function from sample space to R. Now the inverse mapping of the random variable will be a set, and that set must belong to the sigma field that is assumed in the construction of probability, and that must hold for all real number from R. And the set we usually consider here for the definition of random variable is like minus infinity to x, where x belongs to R. So random variable is a deterministic function which has nothing random in that function. Only what will be the input as omega, that is the outcome of a random experiment you may think of. Now, if you consider any function of random variable, then that is also a random variable. And for the same omega, if you can construct more than one random variables, then you can construct a random vector. We have not yet defined what will be the distribution of random vector. But here are a few examples of random variables and their functions. If x and y are random variable, then a into x plus b into y are also random variable for all a, b belongs to R. Maximum and minimum of x, y, they are also random variable. X into y is also a random variable. If y takes value 0 with probability 0, then x divided by y is also a random. So these are the very standard thing. And similarly, you can consider x square is also a random variable, which is a function of x. This way, you can construct many random variables from a given random variable, and that will be the key method of construction of different random variable. And we will see that how we can do starting from the uniform distribution over 0, 1. In next section, when we will study the modeling with random variable or the special distribution of random variable, whatever you say, then you will see that we will develop the entire course in such a way that we can develop any random variable starting from uniform 0, 1. That means over the length in 0, 1, you have the uniform probability distribution. That means the probability distribution is proportional to the length, and from there you can construct any random variable. The process may be a little bit lengthy, but you can construct from there uniform 0, 1. And not only that, there will be also functions which will take you back to uniform. So uniform 0, 1 is the very fundamental concept in random variable, and that thing we will take it for granted for this course. We will define uniform random variable, and from there we will start all those kind of transformations. And also we have introduced the cumulative distribution function, and we have studied their or just stated their properties. That the cumulative distribution function is the unique characterization of random variable, because the input of the function random variable is an outcome of a random experiment. So what outcome will you get from a random experiment? It is not known in advance by definition. So what will be the value of the random variable? That is also not known in advance. So comparing, when you have to compare two random variables, then comparing by its values is not a good choice. You can compare two random variable through its CDF. Whatever we have studied so far, you can compare two random variables through its CDF, whether the CDFs are, ahead of each other. Can you have two CDFs? One is staying above the other. Just from the.
Sir, eventually they will merge to one.
Eventually they will merge to one, but asymptotically also, is it possible that one CDF, so fx is always strictly greater than the other?
No,
Why?
sir, because the area under the whole curve has to be 1. So if
No,
it
fx is the CDF. I am not talking about PDF. So such that the area under the curve is 1. It is the area. Fx is the area. Okay, think about it. Think about it. Okay, so whatever we have learned, CDF uniquely identifies the random variable, and we have seen these four properties. As x goes to plus infinity, it is 1, x goes to minus infinity, it is 0, and it is non-decreasing, and it is right continuous. And we have also stated a special thing that if you have a function which satisfies all these four properties, then there must exist a random variable associated to it. So that is the thing that we have introduced in the previous lecture. Now,
Sir,
yes, please.
sir, can't we say that since the slope of all the CDFs are 0, so there is no point of asymptotes, like they will merge before infinity?
How you can say that slope is 0? You have seen one example. There the slope was 0.
Yeah, okay.
Okay. You have just seen one example. There the slope was 0. But today you will see other example. Their slope is not. Okay.
Sir,
Yes.
so regarding the right continuous, what if we take the right extreme point of the graph?
Say again, please. I couldn't hear
Sir,
you.
regarding the right continuous, I mean fourth point property.
Yes. Yes.
From yesterday's example, what if we choose the right extreme of any step?
Oh, if so, you are saying if I choose this way.
No, sir. The 3p square into 1 minus p. That step. Choose any of the steps, sir.
So from here, you are saying
Yes, sir. If we choose the right extreme.
this part.
Yes, sir.
Or
Then it
this
is not
part.
right continuous.
No. So right continuous mean you have to approach from right. X is
Yes.
going to A from above. X value must be larger than A, and it is going to A.
Yes, sir. But for the right extreme, it is not equal, right?
What do you mean by right extreme?
In the region minus +1 to +3, we have a step, right?
So +1 to +3. So that means you are going to 3 from below. That limit I have not talked about. Left continuity is not guaranteed. Right continuity is guaranteed. Is it okay?
Okay, sir.
Here you are approaching to A from above. That means from right hand side. Do you get my point?
Yes, sir.
You are approaching to this point from this side, not from this side. From this side, whatever is happening, one limit is here, another limit is here. So definitely continuity is not guaranteed. That's why the name is right continuity.
Okay.
Okay. Okay, very good. So let us talk about something new. Okay. So we will consider now we will CDF is common for any random variable and it will always exist, and from here we will have a bifurcation which is very apparent, but for your course we have to do it. So discrete valued random variable or discrete random variable. I hope you can see this right properly. Is it properly visible, right?
Yes, sir.
So I'll share it just after the class, no problem. So discrete valued random variable. So for a given probability space, always we have to start omega, A and P. A random variable X is said to be discrete valued if X of omega, for all omega belongs to the capital Omega, that set is either finite or countable. So that means it is either finite or you can map it with the natural numbers. And the X inverse Si, where any Si belongs to S, that must be an event. So the simple idea here is that if you're mapping from omega to a subset S of R, if the set S is either finite or countable, then we call the value or the random variable as a discrete valued random variable. So here, just so we start with omega script A P probability space, and now you are considering the mapping omega to S, where S is also sometimes called the sample space of random variable. So this is the sample space of a random experiment, and S is the sample space of a random variable. So X is mapping from omega to S, and this, which is a subset of R, and if S is finite or countable, countably infinite, then X is called discrete valued random variable. And it must satisfy the criteria that satisfying X inverse of any number belongs to script A when Si belongs to S, for all Si belongs to. So this is an event. Okay, so this is an event. For all Si, this is an event. So this is the definition of discrete value random. So a very quick example you can think of that omega is 0, 1 and you're mapping x omega to, say, let us call a very simple thing 0 and 1. Remember this thing. So such that if x omega equals to 1, if omega greater than equals to 0 less than equals to p, and it is 0 if omega greater than p less than equals to. Okay. So S, this is S. S has only two values, and in whatever, so x inverse 1 is 0 to p, x inverse 0 is p to 1. So quite simply, x is a discrete value random variable. And can you tell me what is the name of this random variable? I think this much familiarity you have in your 10+2 level, or if you have done probability once before. What is the name of this random variable x? It is the key thing of discrete random variable. In practice, you may not often see this omega. You will start from here, but mathematically you can always think in this way. So can you please tell me what, if you know that, what is the name of this random variable?
Bernoulli distribution.
Yes, this is Bernoulli. Bernoulli. Or often we write in this way, BP. So here you can see that 0 to 1, this set is discretized into two parts, and one part is taking value 1. So probability x equals to 1 is p equals to 1 minus probability x equals to. And this thing you can use, say for example, a switch is randomly on or off, machine is functioning, not functioning, a living being over time is either dead or alive. So all this modeling can be done by this random. So this is the building block of all discrete random variables. Whatever you will see in future, all can be started from here. Okay. So to characterize this discrete random variable, so can you please tell me how its CDF will look like? Just let us do a simple exercise. How its CDF will look like. After doing the exercise of yesterday, this will be pretty simple now. How its CDF will look of x. So in this direction x, in this direction fx. So where will be the jump?
At P.
Say again, please. Where
At 0.
will be the 0?
And at P it will again fall back to 0.
Why P? What are the
Means
values x can, what are the values x can take?
all real numbers.
All real numbers will have jump.
No,
Jump,
no.
where you will have jumps.
Sir, at 1.
Yes, at 1. Correct. So starting from minus infinity, from the definition, it will come as 0. Then how much amount of jump will be here? What will be the amount of jump here?
1 minus p.
1 minus p.
1 minus. And here is the amount of jump is p. So ultimately it reaches to 1 and it will stay at 1. So this is the very simple thing. And okay, so let us proceed. Now, if we can represent this amount of jumps in another function, that is known as the probability mass function or discrete density function. So let me introduce that. So probability mass function. So probability mass function of a discrete valued random variable on a probability space omega AP is a non-negative function which is defined by fx equals to probability x equals to x on R, and fx is always greater than equals to 0 for all x. In the set S, typically fx is strictly greater than 0 and sum over S, small s belongs to capital S of fs is 1. So total probability is 1. That means the total amount of jump is 1 because you are starting from 0 and you are reaching to 1. And for any real number, fx is either positive or 0. And for the sample space of the random variable, S, fx is always strictly greater than 0. So these are the properties of probability mass function. And it is also known as the discrete density function. So let me just write down the same thing once again. Yes, please. Well,
Sir, I have a doubt in this 1 minus p, sir. Like how we got this 1 minus p, I'm a bit confused here, sir.
here.
Sir, yes, sir, yes.
So if you have probability x equals to 1p, the x can take two values 0 and 1. The probability of x equals to 1 equals to p. What will be the probability of x equals to 0? Its complement.
Yes, sir, 1 minus p.
1 minus. Is it okay now?
Yes, sir.
Is it okay? Hello?
Yes, yes, sir.
Okay. Okay. So what we have just told that probability mass function or PMF, this is typically used for discrete valued random variables, and it is a function fx which is strictly greater than equals to 0 for all x belongs to R, and I can say that if x is strictly greater than 0 for all x belongs to S, and sum over fx x belongs to S equals to 1. So these are the three properties must be satisfied by probability mass function. And from here, with this example, it is pretty clear that if you want to see CDF fx f of small x, which is probability x less than equals to small x, is nothing but sum over x f of x, then I can write it as an indicator function. So let me change the notation. This is x, so let me call it t. If t sum over t, and t is less than equals to. So what does it mean? You can take any value t and you compute the value of ft, and this is an indicator function. Indicator function can take value either 0 or 1. So if this condition satisfied, it will take value 1, otherwise 0. So this, it is in general also you can consider any set A, but we have considered the set x less than equals to x. So x is say in this way that x is from minus infinity to small x. So if that condition satisfied, then only it will become 1, otherwise 0. So you can compute the cumulative distribution function as a sum of probability density function. So let me know if you have any query in this notation. So eventually we can write this thing fx, which is x belongs, probability x belongs to minus infinity to x, that you know from the yesterday's definition, and that means you are doing the summation in generic notation that t ft can be 0 or greater than equals to 0, greater than 0. If t belongs to S, it will be greater than 0. If t doesn't belongs to S, it will be strictly equal. I mean, it doesn't belongs to S, it will be equals to 0. If it is belongs to S, it will be strictly greater than 0. Now you can say that in this way, that sum over t ft and then indicator function t belongs to this minus infinity to x. So two things must be positive, then only you will get contribution. Here for to make the summation valid, you can also consider that this belongs to S. Otherwise, you might have difficulty to understand the notion of summation here. In general, it is true and correct, but whatever knowledge you have so far, you can consider t belongs to S. So, do you have any query here?
Sir, if t belongs to S, then it will be countably many. Then t will t also belong to minus infinity to x?
Say again, please.
Sir, if t belongs to x, then it will be countably many. That t will,
If t belongs to S, then it will be countable. Otherwise, in general, I should write integration sign, but that integration is not introduced to you so far. So I am writing t belongs to s. That is why I am writing. So here you can see that ft for this function, so ft is 0. Now if you say, for example, if you are typically interested, say f of say 0.5, okay, so from this point, from the left, if you come, all are 0, then at 0 you have fx, small fx is, so this is f small f0 and this is small f1. So you have an amount of jump small f0, so small f0 at t equals to 0, and then t is strictly less than s. So this condition satisfied, this condition is also satisfied. Then you will get, from this function you will get 1, and from this function you will get 1 minus p. So 1 minus p will be the contribution, and that thing will retain for 0.5. So in this way you will get the probability x less than equals to x. Now for general thing we will be able to extend the same idea without any problem. And one important thing that I should mention here, let me, so in the from previous example also you can compute. Already you have done this work, but so from this example, say for so if you want to see that f of, we have done a long exercise right in the previous lecture. Okay, so this is, you see that this is the way how we have defined. We have go back to this all elements so that we can consider them as an event. But now we know the probability mass function. So these probabilities you can compute through probability mass function. So these are the contributions you have got from probability mass function, and their summation has happened. So already we have done the groundwork, so that today when we are defining the general definition, it should be much more clear to you. And another remark that I should make here is, when we say that discrete valued random variable, it need not be integer. Okay. So here need not be you may have the number, say for example, if you have the all natural number, you can also have n plus 1 by n kind of thing. Or it is just needed that it should be either finite or you have a bijection with the set of natural numbers. That's it. It need not be integer valued. Be careful. Usually you will find all of them, most of them are integer valued, but that technically that is not the requirement that it should be integer. It can be, fraction can be there, but the set must be counted. Okay? Okay. So any query before we define the continuous valued random variable? Any query regarding PMF, CDF, and discrete
Sir.
valued random variable?
Hello, sir.
Okay. So if there is no query, And these are pretty simple thing. You have to be just careful about it. Okay, so here we are trying to have two things together. So continuous, when we talk about continuous valued random variable, we have there many technical things it gets involved to here. But we want to bypass that thing for your course. So we define this continuous valued random variable on a probability space omega A and P. Ax is said to be continuous valued if probability x equals to any real number small x, that probability equals to 0. That means the CDF will have no jump. The CDF fx is a continuous function. More precisely, there is a notion called absolutely continuous. We are not going to the definition for you. Let us consider that x is continuous function such that you can have a differentiation. Absolute continuity is a more stronger notion than usual continuity, and absolute continuity implies differentiability. So here we define the continuous valued random variable with the help of the probability, and we say if fx equals to f of minus x and f of x plus or x minus for all x, then we say that it is continuous valued random variable. So for the criteria of definition, we just focus here that probability x equals to x is probability x equals to x is 0 for all x, and the probability density function to get the probability of such continuous valued random variable, we define a non-negative function f from real line to 0 to infinity, such that for any set, any set of this kind minus infinity to x, you can get that probability in a similar way that you have got for discrete valued random variable. Instead of summation, you have integration fx, indicator function x belongs to a dx. So you can have a notion of probability density function. So here we have to clarify many things which is often confusing. So first of all, let me know what are the queries you have. One by one, I will, whatever I have to say, I will say, and if whatever your queries, I will try to answer. So from this definition of continuous valued random variable and probability density function, what are your queries? First, let me know.
So if
Yes.
the probability of x equal to x is 0 for all values of x, then how is the total probability being 1?
The total probability we are no longer calculating through summation. So there is no problem to have the probability to 1. We are calculating through integration. And whenever you are integrating, you are having a non-negative function f, which is mapping from 0 to from real number to 0 to infinity. And if the integration, that means area under the curve, is positive, or and it is total area is 1, you are done.
Okay.
Okay.
Okay, sir.
Any other query? So here,
Sir, I didn't get that part that if x equals 0 for every real, and how will the function be positive? I mean, it will be 0 everywhere, right?
No,
That then the
here
integral becomes 0.
look. Fx is not probability x equals to x, which was there for probability mass function. Here I am not claiming that thing. That is the fundamental difference. Probability mass function itself is a probability. Probability density function is not a probability. Is it okay?
So then what is f here? Small f.
So small f is a function from real number to 0 to infinity, such that if you integrate small f over this kind of interval minus infinity to x, then you will get the probability x equals to x belongs to a. Is it okay? It is a function, just a function, non-negative function.
So then it can be greater than 1.
Say please. Yes, very fun, good question. Yes, it can be greater than. It can be greater than. So one by one, let us. We have nice questions. So let us try to answer them with examples. So first of all, from the continuous valued random variable, so you have omega a p probability space. X is mapping from omega to R, no problem. Then probability capital X equals to small x equals to 0 for all x. That means there is no jump discontinuity in the CDF. So the CDF will look like this. Typically I am drawing. It can have many other forms. Okay. So this is fx and this is x. So this is how the CDF will look like. It will come from minus infinity and it will go to plus infinity, and here it will start from 0 and it will reach to 1. So if you go from any point, if you go from left hand side and right hand side, these both limit will meet together, there will be no problem. So f of, so let us call a minus equals to fa equals to a plus for all. That thing holds for the CDF. Now to get the CDF, that means f of x equal probability x belongs to minus infinity to x. To get this probability, if I have a function, f is mapping from R to 0 to infinity, integration, say, let us call ft dt minus infinity to x. The same thing I can write in this way, in general, ft, then indicator function t belongs to minus infinity to x. Now I can write minus infinity to plus infinity, or in general let us leave it writing as t. So whatever set you are specifying here, that condition must be satisfied. This thing has to be greater than 0. Then this entire product will give you contribution for the area under the curve. So this is the function, and which is helping us to get the probability x less than equals to x. So this is eventually your probability x less than equals to x. This is how. So this fx is known as the probability density function. Okay, now one question has come, that whether it can be greater than 0 or not. Okay, so we will answer that question. Okay, so let me so just for remark, I am leaving. This is not part of your syllabus. F is absolutely continuous. Okay, so this thing is beyond the scope of your syllabus. At least you remember, for continuous valued random variable, it is continuous at least. At least this much you remember. CDF is continuous. Okay, so from here, so I hope all of you have done Riemann integration. So if you have this identity that fx equals to integration minus infinity to x ft dt, then what will be ddx of fx? Fundamental theorem of calculus.
Sir, fx.
If this thing holds for all x belongs to R.
Small f of x.
F of x.
F of small f of x. Yes. So this is the relation between CDF and PDF. So this is your CDF and this is your PDF for continuous valued random. So if you are given a CDF of a continuous valued random variable, to get the PDF, what you need to do, you just need to differentiate it. If you are given a PDF, to get the CDF, what you need to do, you just need to integrate. That's it. As simple as that. And all for your course, everything will hold under Riemann sense. So whatever you are doing so far, that will be good enough. Is it okay? Any query? Now let us see the example where PDF can be greater than 1, because that is a very much fundamental query, and it is often we see that when in final semester Viva Voce students are asked whether CDF can be greater than 1, many students reply no, but that is not correct. Okay. So first of all, example. Let us talk about the uniform 0-1 distribution. So that is the fundamental distribution. Uniform 0. This is the source of everything. Okay, so we are defining CDF. So usually we write in this way that X follows. This is the symbol is standard in probability and statistics that X follows. Okay. Uniform 0, 1. So this is the lower limit, this is the upper limit. So as I have told that CDF uniquely identifies the random variable. So let me give you the CDF. Fx equals to probability x less than equals to x. This is defined as 0 if x is strict less than 0. It is x if x is and 1 if x is greater. Any query? So how will it look? Suppose here is 0, here is 1. So it will start from left as 0, from here to here, y equals to x line, then always 1. This is the CDF. Perfect. Now you please tell me, remember CDF must be defined on entire R. So it must consider the entire range of real line. If you, nowadays you are having online exam, but in offline exam, if you miss any point to write, strictly cut and 0. One mistake in the definition of CDF and PDF will not allow any partial marking. And that is everywhere followed. Any mistake in writing CDF and PDF, completely 0 mark. And that holds in the interview also. So CDF must be defined on the entire real line. Okay, now you tell me what will be the PDF value. Here is CDF. Okay. So what will be the PDF of this random variable? You know how to get the PDF. So please tell me what will be the PDF.
So from if
X
x
less than
0
0.
less than equal to x less than equal to 1, then it is 1. Otherwise, it is 0.
Okay. So 1 if zero or okay, very good. So how will be the plot? So it will come, then there will be jump. So this length is 1. So this is small fx. Okay. And from here, if I ask this question that what is the probability that x is strictly greater than a? Okay, so tell me all these probabilities. What will be this one? When a can be greater than equals to 0 and what will be this number? You pick up any interval between 0 and 1 as a subset of 0 and 1. What will be this probability?
B minus A.
X.
B minus. So this is the thing. Now let us play the game. Anybody? Yes.
Sir, in the PDF
Yes, yes, yes.
of 1,
I can hear it. So much noise. Please say
0.
which one?
Sir, am I audible, sir?
Yeah, yeah.
Sir, at in the PDF function, at x equal to 0 and x equal to 1, how do we say that it is 1 for sure? Why not 0?
Okay, okay. So the thing is that even if you remove this equality, the entire thing will hold, because at one point the probability is 0. Fx is 0, but there is no jump. So if you write x, this is also correct, this is also correct. No problem with that. Okay. Both are okay.
Okay.
Okay, so now let us start the jugglery with it. Okay, so let me define. Should I use another page? I think that will be better. Okay, now example 2. I am defining, as I have told that most of the simple functions of random variables are random variable. I am defining x is following uniform 0, 1. You know its PDF and CDF, everything well. Now I define y equals to 0.5 into x. I can do that. Okay. Now, can you please tell me what is the PDF, CDF and PDF of y? So how will you approach? First you tell me how will you approach? So to address this kind of problem, it is a very common type of problem. What you need to know, first you know that x belongs to 0 to 1. And y equals to 0.5 times x. So y belongs to, what is the possible range of y? What can we
0
do?
to 0.5.
0 to
0 to half.
0 to half. Correct. So here you have to be careful, rest of the part will be trivial. Okay, now calculate the CDF. F of small y equals to, so let us call in this way, that f of y of small y, that means probability y, probability y less than equals to small y when y belongs to 0 to 0.5. Okay, very good. But you know y equals to 0.5x. And from here what you know, x less than equals to 2 times small y. Correct. Now, what is the CDF of x? So this is eventually f x, sorry,
2y.
2y. So the CDF of x is looking like this. So this is equals to 2 times y when y belongs to 0 to 0.5. Okay, now let me make it complete. As I have to define it for the entire real line, fyy equals to 0 if y is less than 0, equals to 2y if y and 1 if y is strictly greater than 0.5. This is the CDF. Now quickly tell me what will be the value of PDF or expression of PDF. So what will be f y?
So 0 and then 1 and then again 0. Sorry, 2.
0
So,
to
0 or 2. So it will be 2 if y belongs to 0 to 0.5 and 0 otherwise. Now the answer is clear that PDF can take value larger than the area under the curve should be less than 1. That is which is probability. So PDF is not probability. Is not probability. It is not probability. So eventually the function, whatever the PDF function you will have, maybe something like this. Then the area, this height is the PDF, then the multiplied by say delta x fx. So delta x fx, this is approximately probability. Now delta x fx summation, that is integration, and that is probability. Is it okay? Any query? Any doubt? Let me know. Anything else that I should cover? PDF. So another thing, just let me tell you that. So here, to get probability from PDF, what you do in this way, that either you multiply fx with this small delta x and then take the sum and the limit, which is integration. But for PDF, probability mass function, what you do, you multiply 1 and then take the sum. So let me just tell you what it is. So for discrete valued random variable fx, say in general like this, you can compute in this way, that small fx into 1 and so let us call ft and sum over t, and t less than equals to x. For discrete valued random, a continuous valued random variable, fx is integration ft dt minus infinity to x, which is again sum over say delta x fx delta x, and this range is going from minus infinity to x. So here the multiplier is delta x, what in integration or t you can say, no problem, dummy variable delta t. So this multiplier is delta t, and this is pdf, this is pmf, and this is 1. So here you are, as you are in a countable set, you multiply 1, 1, 1 and then take the sum, and this is probability, this is not probability. Okay. But in general, it is called discrete density. This is called the usual way density. This is also called discrete density. There is technically nothing wrong calling it discrete density. Okay. So for you, remember this thing as PMF and this one as PDF. So that is the basic thing. Don't get confused. And PMF is probability, total sum is 1. PDF is not probability, but integration should be less than. That's it. Okay. Before we move forward, any query? Well, if you have any query, let it clarify, because we are entering something new.
sir.
Yes.
Sir, in the very last formula,
Uh-huh.
sir, shouldn't
This
it be t running from minus infinity to x?
Uh, uh, this one.
Yes, sir. Yes, sir.
Ah, yeah. Yes. T running from one. Correct.
Okay, sir.
T running from one. Anything else? Okay. Then let us move for another interesting thing. So now you can claim for your course CDF as well as PMF for discrete valued random variable and CDF as well as PDF for continuous valued random variable uniquely identifies a random variable. So if you know this either CDF or PDF or either CDF or PMF of a random variable, you know everything about the random variable. Okay. For higher courses, PDF is not so reliable thing, but for your course, everything can be done with PDF. So now we are going to introduce another interesting idea, which is known as expectation. So let us do some introductory part for that. So, have you studied moment in physics? Can anyone tell me the definition of moment? Moment from physics. So suppose you have a string from 0, so this is a distance 1, this is say distance 2, this is say distance 3, and maybe say this is distance 4. And here acting force W1, here acting force W2, here acting force W3, here acting force W4. So where the resultant force will be working? Tell me. So this is the origin, it is hooked here. Where the resultant force will be working?
Somewhere between D1 and D4.
D1 and D4 definitely. And what will be the formula for that?
Summation
WD
DAW.
divided by summation W.
Yeah, divided by summation.
PIWI, sum of that. Okay, at this location, you can think that all forces are acting maybe somewhere here nearby, say let us call. At this location it will be acting. Now if I change the story in this way, that you have the same thing, here it is 0, here it is D1, here it is D2, here it is D3, here it is D4, and for x is a random variable, probability of obtaining D1 is P1 probability for getting D2 is P2, probability of getting D3 is P3, probability of getting D4 is P4. Okay, so probability of say x equals to di equals to pi. Now, where you can think, so if you go by this formula, where you can think the entire mass will be gathering. So if I write di pi, sum over, just replace w by p, sum over pi. But sum over pi is 1, their probability. Okay? So this is known as first order raw moment and usually denoted by m prime. Okay. Or maybe you can theoretically also say that mu prime. So let us define in this way. So this is the idea of calling. So here you can think that the value multiplied by the probability, that is known as the moment. And now you can generalize this idea. So rth order raw moment. So let us call, okay, so let me call it mu prime, otherwise there will be confusion. Mu r prime in this way that di to the power r pi, I running from, say over I. But to define this thing, we have to be little bit careful because there are some technical problems will arise. Okay, so what are the technical problems that can arise? Let me tell you. First of all, let me give you the definition and then you will realize why I am talking about some technical difficulty. Yeah. So this moment can be generalized, so that you have seen the first order raw moment we have defined, and then we can talk of any rth order raw moment. So the first order raw moment, theoretical moment, that is known as the expectation of a random variable. And the expectation of a random variable with CDF, random variable x with CDF fx, is defined as, this is the generic notation. Some books follows this notation, such that they can define it for discrete valued random variable and continuous valued random variable together. So the meaning of this notation is something like this, that it is sum over x fx if x is discrete and integration x fx is x is continuous. So both of the things to write together, this is the notation. But you have to be careful that this condition satisfied for discrete valued random variable and this condition satisfied for continuous valued variable. Why these two conditions, or individually this condition to be satisfied? If it doesn't satisfy, what kind of problem you may face? From this example, it is, well, you can immediately extend the idea. Replace summation by integration, do whatever x fx dx, or do the summation x fx. That is all right. But why we are focusing on this criteria? Any answer? If this condition doesn't hold, then what can happen to this summation?
Sir, so that sir PDF tends to 0 as x tends to infinity.
Of course, PDS must go to 0 as x goes to infinity, otherwise it will not be summable series. That is correct. But why this absolute value? So take the example, this second example. Can you say something?
If we do not take mod, then denominator can become 0.
No, PDF is defined. What will be the problem in expectation?
It may become negative if we do not take mod.
Which one will become negative?
Expectation, because x can take any value.
X
is positive.
fx is always positive by definition. X can take any value, positive or negative, according to this set S.
But negative expectation, it doesn't.
Why? There is no restriction on expectation to become negative. Expectation can be negative. Never told that expectation cannot be negative. Well, at least series thing you have done, right, in your Math 1, Math 2? So let us compute this one and let's try to see. So example. So fx is 1 upon mod x 1 plus mod x. First of all, and x is x belongs to S, where S is minus 1 to the power n into n, where n belongs to the natural number. Okay, so what will be this quantity? X fx. First element, minus 1 divided by 1 into 2. Second element, 2 divided by 2 into 3. Third element, minus 3 divided by 3 into 4, and so on. It is going. Is it okay? Okay, so
yes, sir.
Can I write this thing like this? 1 minus half plus 1 by 3. Sorry, 1 by 3 minus 1 by 4 plus 1 by 5 minus 1 by 6, so on, continuing minus 1. This one I have introduced, so I have adjusted. Okay. Now, tell me what will be this value.
ln2 minus
Sir,
1.
log 2 minus 1.
Okay. This is, you know, log 2 minus 1. Now, if I say that this summation I will do in this way. That now there is a question mark. 1 plus 1 by 3 plus 1 by 5 plus 1 by 7 dot 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 minus 1 by 2 plus 1 by 4 plus 1 by 6 dot 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 minus 1. Can you tell me? I have not done anything, just rearranged the numbers. Anybody? Any answer? I have just rearranged the numbers. Can you tell me what will be the conclusion from this expression? Where this series will go, can you tell me?
Divergence.
It will go to infinity. It will also go to. So no conclusion. So to avoid this thing, so no conclusion. So to avoid this thing, that the rearrangement of the series or integration can give us different values for the same series or integration. So to avoid that, we need the condition of absolute summability. If a series is absolutely summable, then it is also summable in usual way. But if it is conditionally summable but not absolutely summable, then you can rearrange the series or rearrange the integration in such a way that you can make it converging to some different points, or maybe you can make it divergent, or maybe you can make it inconclusive. So to avoid all those trouble, we restrict first the absolute summability. If absolute summability is ensured, then only we can define expectation. So anybody has any query, any doubt that this will be divergent? If you have doubt, let me know, I will prove it. Any? If you don't know, then let me know. It is a very simple proof, 2 lines. We can do it in the class. Or if you know from your courses, then it's also fine. So, is it fine to everybody that this series 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, this diverges? Do you know the name of this series?
Harmonic series.
So then I hope it's fine.
Sir,
to
can
all.
you prove it?
Okay, so let us prove it. It is a very simple proof. 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6, 1 by 7, 1 by 8, 1 by 9, dot, 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 1 by 16. So you write everything. Now I am replacing this quantity with a lower number, 1 plus half. Then for these two numbers I am replacing by the least value, 1 by 4, 1 by 4. Then this for 4 values I am replacing by the least value, 1 by 8, 1 by 8, 1 by 8, 1 by 8. Then for these 8 values I am replacing by the least value, 1 by 16, all values 1 by 16, 16. And so on, we will be clubbing together and we will go on. So this number is 1 plus half. From here you will get half. From here also you will get half. From here also you will get half. So this will be a series of half, 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 half. It will going to infinity. So this is a number from which this is smaller, and that summation is going to infinity. So definitely this sum is going to just 2 lines. Is it okay?
Yes, sir.
Okay, so this is the idea of why we restrict ourselves for the uh, absolute convergence. So you can also try this example. Apparently it will come as expectation will be 0, but that is not true. If you take mod and mod of x fx dx, integrate it, it will not converge. So expectation will not exist for this density function. So first one is for continuous value random variable, second one is for discrete value random. Okay, now let us define the moment theoretically in general, that expectation of, okay, so mu r prime, expectation of x to the power r, okay, expectation of x to the power r, if expectation exists. If expectation exists means those two conditions, if it is discrete, absolutely summable, if it is continuous, absolutely integral. That means expectation exists. So this is known as the rth order rth order raw moment. Okay. Now mu1 prime usually written as mu, and it is the mean, which is expectation of x if exists. Now when we have the notion of rth order raw moment, another notion is there, which is something like that, mu r, which is expectation of x minus mu whole to the power r, which is known as the rth order central moment. So central moment means mean subtract. Can you please tell me what will be mu1? What will be mu1?
0.
0.
Zero. So it is it carries no information. Okay, mu1 doesn't carry any information, but mu2 is expectation of x minus mu whole square, which is eventually, if you expand the square and take the expectation, that expectation of x square minus 2x mu plus mu square. Then if you take expectation inside term by term, and that will hold trivially by from definition, expectation of x square minus 2 times expectation of x. Mu is constant, so expectation will not impact on it, mu square. So it is expectation of x square minus mu square. So it is expectation of x square minus expectation of x whole square. And this is known as the variance of x. So I will come back to this name once again. So second order central limit. And square root of variance of x is known as the standard deviation. Usually denoted by sigma, and variance of x is usually denoted by sigma square. This is a very common notation. I hope if you are familiar with probability, you know this. So this is the notation of mean, and this is the notation of variance, and always if exists. Whenever it exists, then only we can talk about it. Okay. So now, how much time I have? So let me go for the interpretation of this thing, mean and variance. Another interpretation. So data-driven interpretation. So suppose I ask you, any one of you, that how much marks you have got in 10 plus 2 level. What will be your answer? Anyone, please reply. Suppose I ask this question, that how much marks you have got in 10 plus 2 level. Usually, how will you reply?
Weight at the end of 10 plus 2 level minus weight at the first beginning of 10 plus 2 level.
Why? No, well, simply no, nothing complicated. Just tell me what is your score in 10 plus 2 level. What will be your reply? Just tell me. Anybody?
Mean of all marks in board exams.
Okay, so you, so whatever, maybe say you say that, say 92%, 98%, something like that. So you tell us the mean of the marks. Then question is, why you tell us the mean of the marks? More precisely, why do you think that the mean will be the well representative of all your marks? So say for example, you say that total score is say 97%. And can you please tell me that say language 1, how much you have got? Say let us call M1 marks you have got. What are the subjects you nowadays have? Language 1, language 2? Okay, so language 2, M2 you have got. Then physics you have got M3. Chemistry you have got M4. Mathematics you have got M5. And biology, say for example, or you don't have biology, say M6. In our times we had all this. Okay. Now you see, most of you, whatever the number mean you are saying, neither of them are exactly equals to this number. Right? For most of you, I think it will happen that neither M1 equals to this, nor M2 equals to this, not this, not this, and not this. None of them are equals to that number, but you still give me this number as a well representative of all these numbers. Why? Is the problem clear? Hello?
Just to get an average understanding of like how well we have done, because even though the marks may not be equal, but then they might be just near around that mean area.
Okay, marks need not be equal, that is very correct assumption. Okay, near about this number. So let me make it precise. So suppose I am replacing, so what you are doing, you are replacing this number by this, 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 and so on. So if I replace all the number by a single number, say A, then I am committing some error, right? If I replace each of the different numbers by a single number, then I am definitely committing some error. So let me measure the error. So, and let us call that error as L2 is sum over mi minus a whole square. I running. So in general, let us call I running from. So this is the error. So for what value of a this error will be minimum? For what value of a this error will be minimum?
When A is mean.
Yes. So how do you get it? Yeah. So when a equals to, say, let us call m bar here equal to 1 by n sum over mi. So you just there's a very nice function, you can differentiate it, equate with 0 and calculate it, and it check the minimality condition. So mean in that sense is minimizing the square error. So this is a square error, or sometimes known as the Euclidean error or Euclidean distance. So that when the Euclidean distance or the square error is minimized with respect to mean. Okay. Now I am defining in this way that mu already we have defined is expectation of x. Its sample version, this is theory, sample version is m, so mu1 prime equals to mu. So m1 prime is 1 upon n sum over xi. If xi's are the data, it is x bar. Sample mean. And it is theoretical mean, known as expectation. Okay, similarly, if you now replace this quantity, you can also consider this divisor, no problem. The answer will remain unchanged. So mu2 is variance of x, is sigma square, that you know. Sample version, let us call for the time being as s square is 1 upon n sum over xi minus x bar whole square, iron. Okay. So just I have in place of m for this example, I am writing x in general and x bar is the sample mean. So this is the sample version of variance. Now, what does it say? This interpretation we have got, square error is minimized, and that minimized error is the sample variance. So this is the minimized error. Minimized square error. It has many other interpretations. So this expression one upon n sum over xi minus x bar square iron. It says that how the data are scattered around the mean. So how the data are scattered around the mean. So you can see that from mean the squared deviation is calculated and average is taken. Another interpretation is the mean of the squared deviation is minimum. So this mean expectation, mean of squared deviation is minimum when measured about x bar. So that is the interpretation. If a equals to x bar, then the square deviation is minimum. Mean of the square deviation. Another interpretation from here you can follow. Let me see that you can write the thing in this way. I running from 1 to n xi minus x bar whole square. This quantity is same as 1 by 2n square double summation I and j xi minus xj whole square. These two things are same. You should be able to show it. And the interpretation from here is that this is also a square, measures the scatterness the data among themselves. That is not clear from here, but from this expression it is clear. Xi minus xj whole square, I running from 1 to n, j running from 1 to n, double summation. So for any pair you choose, their difference among them, square difference, and their average. So it is also have this interpretation that how they are scattered among themselves. So I am leaving this one as a homework. It is a very simple exercise. Just the trick is you write in this way that I running from 1 to n, j running from 1 to n, xi minus x bar, sorry, xj double summation ij 1 by 2 n square xi minus xj whole square. The trick is only this. You can write xi minus x bar plus x bar minus xj whole square. So you take this thing together, make the expand the square, take the sum. I'm leaving this one as homework. So we have yeah, and then you take the sum, you will get come to this expression. So whatever we have studied today, we have defined the discrete random variable, CDF and PMF, continuous random variable, CDF and PDF, and we have talked about the moments in general, and we have also talked about the interpretation of mean and variance. So before leaving, let me just tell you one more thing. So mean is a measure of central tendency. Mean is a measure of central tendency. Where the data is centered, and standard deviation or variance is a measure of dispersion, how they are dispersed. So there will be other alternative measures also. So another homework you can take, that if you take the absolute value where the minimum will occur. Another homework. If we write sum over 1 by n, say xi minus b, I running from 1 to n. If this is the expression, where the minimum, for what value of b the minimum will occur. So this is another homework I am leaving. I am asking you to write a computer code. You take some 5-10 numbers and you find out the solution and tell me in the next day what are your observations. Even if you cannot say the correct answer, doesn't matter. Your observations are important. Okay. So take any few numbers, 5, 10, 15, and you write a code which will minimize this expression 1 upon n sum over xi minus b absolute. And let me know what you think. So we will talk more about the moments in next week. Okay. Before we leave, any query? Any query? Okay. If there is no query, then thank you. See you on next week.
Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
I will upload the
Thank you, sir.
PDF as well as the handwritten note. Don't worry. And please don't delete the notes or video lectures, okay? It is for everybody. Okay, see you. Prepare well for the upcoming exam. I hope all of you know the date of exam and the timing. Your slot will have the first exam. So be prepared well.